6 zeros min. And
can you just register 6 Cs and then site admin?
sorry, well, no, because if you registered 6 Cs and then site admin, the S would line up with the beginning of here rather than here. So you need this first block that has the unknown plus the first 6 letters. Yeah, exactly. So when we register those, that's what we get. So you can see the blocks that we're interested in are highlighted. We want the site ID block from that one, the MIN block from that one. The other stuff, who cares? So now we can impersonate that user theoretically by combining those two blocks that form the username, and just using the remainder of the token. I think we just picked the remainder of the token from one of those other blocks because we didn't think that it mattered. And lo and behold, it didn't matter. You change your EE cookie to this value, base64, and code it back to its original form, of course, and then you're able to access the application as that user. So here's the interesting part. Thinking back on that attack, what we just did was successfully subverting the authentication mechanism and breaking that crypto without any knowledge of what algorithm was in use, what the key was, what the key size was, anything really, other than all we did was look at some patterns in the ciphertext and make some observations and do a little bit of analysis to try and figure out where something was, but really, we don't know anything about the crypto other than the mode that was used. This could be AES with a 256 bit key. I don't know. So the primary failings here are, number one, the algorithm mode. So using ECB mode instead of something else. So we were able to kind of take blocks from different tokens and just kind of stick them in at will without modifying the rest of the token. And the other thing is just there's no verification mechanism to kind of for the application to associate specific values of the cookie with a particular username. They're just decrypting what's coming over and finding that known location in the plain text and saying, okay, this is who I am. So in conclusion, ECB mode should not be used. Blah blah blah. I'm not going to talk too much about that because we have more interesting case studies. So a stream cipher example. That was a block cipher. We can find similar weaknesses in stream ciphers using the same good old pattern recognition techniques. Okay, another different application. In this case, we found a bunch of tokens in URLs that we didn't know what they were. And they were all over the application. It wasn't just one cookie. It was parameters that were passed back and forth with requests. There was one called statement, one called file, context, and there were a bunch of others that in a similar looking format. That's not to say that they are the same format, but we're kind of doing reconnaissance on the application. For all intents and purposes, they're the same. So what we noticed is that, first of all of them changed every time we logged onto the application, and they were never the same for any 2 sessions or any 2 users. So that's just an observation at that point. It's not really telling us a lot, but it's something to kind of keep in the back of your mind. So again, it looks like we're looking at base64 here, and we're going to choose to start out with this one that's called statement. This lets you look at this was kind of a page where you could see your previous bank statements, and when you click over, there was a link, and it would show like the statement number, and then the actual link had this parameter in it, this long thing that theoretically maps up to the original statement ID in some way. So here are the base64 decoded values for several of those different statement tokens. So just looking at a first glance, you see some similarities. Above that underlined, in each case, I have what the actual statement number was as presented by the web app. So we can use that to start drawing some correlations between the plain text and the ciphertext. If it is ciphertext, we don't even know at this point. So staring at that for a little while, definitely longer than a few minutes, that jumps out at you. So some of the statements, and it's lucky for us that the statements were numbered in this weird way where some of them began with completely different ranges than the others. I'm not sure why that happened, but regardless of that, when it starts with 704.432, we notice a corresponding chunk in the cipher, let's just say the token for now, in the token, that kind of maps up to that. So every time I have 704.432 in the plain text, I have 8B whatever in the ciphertext at that particular location. Similarly, when I have 673.199 as the start of the statement number, I have that corresponding blue chunk at the same place in the token. So that gives me a good idea of where the statement number is represented in the token. So now let's take a look at the remaining 4 digits of the statement number and see if there are any parallels there. Appreciate this slide. It took a long time to make. So when a 1 appears at position 7 in the plaintext statement number, you see an F6. This is the green one we're looking at in the token. And you can draw similar parallels for other bytes. So when there's a 0 there, there's always an F7. Oh, look, 0 is F7 and 1 is F6. Interesting. When there's a 7 at the last character, the yellow, there's a 26 there. So you can kind of see that we now know exactly where those 10 characters are in the token that represent the original statement number. The other thing to realize here, I mean, you know it's a stream cipher because my slide at the beginning said stream cipher, but now what we're looking at is you can definitely see correlations, single byte correlations between the plaintext and the ciphertext, and that gives you an idea that this is not a block cipher. So this may be a stream cipher, or maybe this is just an XOR with just a long static string. The interesting thing there is that it doesn't matter to us. If it's a key stream that's generated by a stream cipher, it's still a long list of things, a still long list of bytes that we're going to XOR. So,
they use the same or no initialization vector for all of them.
We don't know. I mean, you can get
But not different for every single one. Otherwise, you wouldn't be able to.
Right. There's not a different initialization vector for each one. That's right. But in terms of whether they're using one at all, you can't tell. You just get a key stream. So we've made that kind of observation now between the plaintext statement number and the token. So let's try and figure out what the key stream is. So we know that in a stream cipher, the plaintext and the key stream are combined together using XOR, and that's how you come up with the ciphertext. So we know 2 of those things, and with XOR we can find out what the other one is. So we know that we know what the token looks like, and we know the 10 bytes that represent the statement number, we think. So we XOR that with the ASCII equivalent of that plaintext statement number. So what's in green there, 37, 30, 34, 34, those are the ASCII values representing those digits. And you XOR those together, and you get the 10 bytes shown in blue that I've labeled partial key stream. So we think that that is at least 10 bytes of the key stream, offset by however much into the token. We'll just do a sanity check just really quickly, and just make sure that if we take that partial key stream, that we think is a partial key stream, and we XOR it with those corresponding bytes in one of the other statement tokens, that we do in fact come up with the ASCII value that corresponds to the plaintext, and you can see that we do. So that's all great and everything, but we've got a bunch of statement numbers, and we can XOR all day and not really get anywhere because it's the statements are still at the same location in the token no matter what, so you're not really getting anything beyond those initial 10 bytes. And while 10 bytes is great, it doesn't help you decrypt other things. So this is where it comes in handy that the application used a bunch of those different similar-looking tokens that I mentioned. So I mentioned the statement and file and context and a bunch of others. So we said, okay, well, maybe these are encrypted using the same key stream. That's a common mistake, so let's try that. So we take one of the context cookies that we found. Actually, it was a parameter, not a cookie. But we take that, we XOR that with those position of bytes of the partial key stream that we've recovered, just to see what it comes up with. Maybe it'll come up as garbage, but it turns out that it comes up with ASCII. So cool, right? You can kind of guess what might possibly come before that and what might come after it. It also helps that when we were on the app, that when we captured this, particular token, that we were actually on the personal information page. So even if you aren't very good at Wheel of Fortune or whatever, you still kind of know what it is. So here's what we can do. We can start to derive more of the key stream based on things that we can guess. So we're going to guess that the plain text, at least part of the plain text there, is personal information. We still don't know what's before it or after it. But what we can do now is we can get that many more bytes of the key stream by XORing those things together. So now we've gone from our original 10 bytes of key material to gaining an additional 2 bytes on the front and an additional 8 bytes on the end. So now we have 20 bytes of key material. Great, but we still don't have all of it. So you just kind of go through this process iteratively. In this case, took the one token called file, took our 20 bytes of key material that we know, decrypted it, and came out with what you see in green there, more ASCII. And this one, you can sort of guess some of it. Maybe not be able to guess what's at the beginning, but it helps that as end users of the web application, we knew that we were looking at a part of the application called Help Center. It was just providing frequently asked questions or stuff about this particular page that we were on, which was paychecks. So we'll guess a few more bytes, 3 more in the beginning, 4 more on the end, and now we've got 7 more bytes of key material. So that's the last iteration that I'll actually go through on the screen here, but needless to say, we had a lot of tokens to go through, and eventually, we were kind of able to derive, just through inference like this, enough of the key stream, using those different tokens, enough of the key stream to be able to deal with any length token that the application was creating. So again, we don't need the whole infinite key stream. We only need as much as the application requires for the longest thing that it's encrypting. So eventually we got, I think that was about maybe 150 or 200 bytes of key material. And then we could kind of decrypt everything, all those tokens in the application, and kind of start to try and understand what was going on, what the application was actually passing around now. So statements was the first thing we kind of looked at. And the fully decrypted statement tokens were structured as follows. And if you remember from the earlier slide, values with specific delimiters. So we have a bunch of numbers separated by pipes, and that's probably what the application is parsing on to break down those particular fields. So we have a number, we don't know what they are, or what their significance is, rather. Statement ID, number, and then some letters. So, the first thing, again, go for the slam dunk first, and then if not, then actually go back and try and think. Will the application just let us replace the statement number with another valid statement number and view the contents? So replace one of the